In full screen. Yeah, good morning, everyone. Welcome to the fourth International Women Days in Statistics and Data Science. I'm very happy to present our session 110, Embracing Complexity, Advanced Statistics and Computational Methods in Modern Data Analysis. And I'm very happy to introduce our fourth speaker, Dr. Zhuan Ma, Dr. Nadisha Yarawira, and Dr. Thelini Jayansinga, and me. So without further ado, I will start with the first speaker, Dr. Zhuan Ma.
Okay. Okay. Oh, hello, everyone. Can you hear me? Oh, okay.
Yeah.
Hello, everyone. So today I'm going to talk about the Bayesian nonparametric hypothesis testing methods on multiple comparisons. So this is a joint work with Qiu Chen Hai. Okay. Because we know multiple comparisons are crucial in various scientific fields. And in the parametric test, we can use a t-test or ANOVA test. However, the parametric tests are often rely on the specific assumptions about the population distribution. And another common way we can use it for the non-parametric tests. For example, we can use the Wilcoxon sign rank test, Whitney-Wilcoxon, and crucial Wallis test. These non-parametric tests do not depend on the distributional assumptions and can provide available alternatives. And a common decision rule for rejecting or failing to rejecting the null hypothesis is we base on the check if the p-value is less than or specific significant level alpha. And this decision rule could usually help to control the type 1 error. However, it provides a little insights into the null hypothesis if it is not rejected. So these observations motivate us to investigate the Bayesian hypothesis testing as a viable alternative to the p-value approach, because Bayesian methods can facilitate the quantification of evidence in favor of both hypotheses. Okay, so first of all, we set up the notations. We let py given theta stand for the likelihood function for the data y, and pi j is a prior for the theta j under both null hypothesis and alternative hypothesis. And we let the prior probability sum equal to 1. And we also define the base factor between the alternative and non-alternative as a weighted average likelihood ratio. So in the Bayesian framework, our decision rule will be the null hypothesis will be rejected if the base factor exceeds a certain threshold. So if the base factor 1, 0 is greater than 1, that means that we in favor of the alternative. Otherwise, the alternative is preferred under a 0-1 loss function. However, unlike the p-value approach, the base factor may fail to control the type 1 error and therefore result in different decisions compared to parametric and non-parametric tests. And so we here we can come up with the base factor based test by integrating the ideas from the two papers, Yu and Johnson in 2008 and Goddard and Johnson in 2016. So we will obtain the base factor using 3 nonparametric test statistics. Okay, so for the base, let me see if I can. Don't know why I cannot make it full screen.
On the Zoom item on your drop-down, there's an expand arrow. If you'll go back to that menu.
Oh,
Yep, there you go.
I see. Thank you. Yeah. For the one sample or paired sample test, we developed a Bayesian-based Wilcoxon sign rank test. Okay. And here we have a critical value. We use tau alpha divided by 2 star instead of the traditional tau alpha over 2. And we also get the corresponding evidence threshold delta t. Well, for 2 independent samples, we also get the base factor based on the Mann-Whitney-Wilcoxon test. Okay, we also derived our standardized critical value, omega star alpha over 2. And also we can derive the corresponding evidence threshold. Well, for 3 or more independent samples, we derive the base factor based on the crucial Wallace test. And also we get the corresponding evidence threshold for this base factor. And then we implemented the simulation studies to demonstrate the performance of our proposed base factor method based on the nonparametric hypothesis test. So due to the time constraint, here I will skip the simulation studies and only show the real data application. So these 3 base factor, along with their evidence thresholds, depend solely on the nonparametric statistics and their associated critical values. And these base factors can be easily computed by adding one more step after conducting the hypothesis testing using the nonparametric statistics. And so for the decision making, if a base factor is greater than its corresponding evidence threshold, that means our null hypothesis will be rejected. However, if a base factor is smaller than the threshold, then we fail to reject the null hypothesis. And so we carried out 3 real data applications. First one is a paired samples. So we used the Wilcoxon sign rank test, the nonparametric test statistic, and we get the p-value is 0.039, so which indicate we reject the null hypothesis at a 5% significance level. And when we use our proposed base factor method, we can also see the data are about 2.5 times more likely to be generated under the alternative than under the alternative, so suggesting rejecting the null hypothesis since the base factor is greater than its critical value. Okay. And for 2 independent samples, we can also see the nonparametric test and our proposed base method also have the same conclusion, fail to reject the null hypothesis. And also, based on our Bayesian method, we can see the data are about 0.75 times more likely to be generated under the alternative than under the null hypothesis. And for the 4 independent samples, they also reach the same conclusion for the both the nonparametric and Bayesian method. And also our proposed method give more information. The data are more like 565 times more likely to be generated under alternatives than under the null hypothesis. Okay. So in conclusion, the developed Bayesian procedures enjoy several appealing properties. So they solely depend on the commonly used nonparametric test and their associated quantities and can be easily computed, and also allow for the quantification of evidence from empirical data in favor of the null hypothesis. So this is an advantage compared to the frequentist method. Okay, so thank you, and that's all for my talk. And if you are interested in more details, you can check the first reference. So this paper has been published in the Computational Statistics. Thank you.
Great. Thank you so much, Dr. Ma. In the interest of time, if you have questions for the speaker, please feel free to use the Q&A chat to interact. I would like to move on to my talk to make sure that we end on time. So here's my screen. Can you see my full screen? Oops. Okay. So I hope you can see my full screen.
Yes.
I am the second speaker. Thank you. In my talk will be over Bayesian adaptive lasso quantile regression with non-ignorable missing responses. My talk is the joint work with Dr. Ranran Chen, Dr. Kei Ye, and Dr. Min Wang at the University of Texas in San Antonio. So a little overview of our problem. We are motivated because in real world application these days, we commonly see missing data and they are happening due to various reasons, most of the time inevitable. And we have different kind of missing mechanism of such data. And usually we see that the one not missing at random is the one that is quite challenging to work with. Some existing method to handle and tackle this type of data, not missing at random, usually require the data come from some kind of reproductive dispersion distribution family that will lead into having some kind of non-robust statistical inference if we do have outliers present in our data. So our approach present a fully Bayesian hierarchical quantile regression modeling so we can simultaneously estimate and select variables that are significant and useful using adaptive lasso penalty so that we can guard against outliers and the presence of heteroscedasticity in the data. So a little bit more detail on our methodology. We devised an efficient Gibbs sampler that can update three main components of our modeling scheme. First one are the parameter relating to the quantile regression model where we use the asymmetric Laplace likelihood. The second block would include parameter constituting and relating to the adaptive lasso penalty presented by the Laplace independent priors. And then the third one, the most important thing to handle missing data is the non-missing at random indicator and also generating the corresponding latent response variable using the non-central T approximation to the logistic distribution and the multivariate normal distribution respectively. To make the computational efficiency, we utilize the conjugate representations of all of the listed components. In the specific, we use the normal exponential representation of the asymmetric Laplace and the Laplace distribution. We also use the normal gamma for the non-central T approximation of logistic. These things allow us to have fully conjugate Gibbs sampler for every single step. Therefore, our computational cost is linear in the parameter space, OP. A little bit on the simulation study to verify the numerical efficiency of our problem. We conducted different type of study, but we want to kind of show here a scenario where we have moderately correlated predictors, slightly higher dimension when we have 10 more predictor compared to our observation. We have somewhat of a sparse model when the first 10 coefficients are non-zero and the last 200 are zero. We have around 25% missing rate in our responses here. So we look at the root mean square error for parameter estimation and the posterior frequency of certain variables being identified as zero. We just randomly select the first 5 non-zero to show here that we kind of see that most of the time our true positive rate is doing quite well. A little bit on our real data application, we look at the prostate cancer data. First study in Tipsharani in 1996 for his seminal paper on LASSO penalty. We have 97 male patients about to have some kind of prostate cancer treatment. 8 predictors lead to 1 response where we look at the level of prostate antigen. This data set actually did not have missing data, but since it is of high interest, we artificially remove some observation with a threshold under 1.1 or greater than 3.8 to generate our non-missing at random, resulting in around 20% missingness in the response. We look at the mean square predicted error of over 10-fold cross-validation at 3 different quantile, like 3%, 5%, 30%, 50%, and 70%. We compare our work, title new here, with another Bayesian method that's preceding this work using quantile regression, but did not treat for missingness, especially missing at non-random, and the quantile regression using LASSO in the frequentist approach. So we do not outperform at every quantile, but we do provide kind of competitive performance here. So to wrap up this talk, we introduce a fully Bayesian adaptive LASSO approach to look at data set with non-missing at random responses through the quantile regression. We are currently looking at the case where we have higher P to N ratio because we do see our model is pretty modest in the burden of imputing the responses that's missing. That will significantly widen the gap between N and P. And we're also looking at imposing necessary constraint so that we can ensure that our quantile models do not cross each other. And thank you very much for your attention. In the interest of time, I would like to also promote the next speaker, Dr. Nadisa Charawira, and she'll be discussing her work with us. Thank you.
Can you see my screen?
Yes.
Okay, great. Okay, thank you so much for the introduction and good morning, everyone. So fast, it's morning. Today I'm going to present one collaborative work with Yanshu Wan and Jiansu. And so I'm going to talk about the dynamic Bayesian spatiotemporal modeling for the real-time disease forecasting with specially likelihood-based weighting. Okay, so after the COVID-19 pandemic, many disease-based authorities has to focus on to prevent the pandemic, especially for the public health. So they have to face several challenges, especially how they are going to analysis based on the population density. Actually, the infectious disease data is very crucial for early outbreak detections as well as the prediction. So there are some other traditional methods they use earlier, especially stochastic process control in the QSAM charts. These methods are reactive. They detect changes after they occur. They mainly focus on the detections, but not only for the prediction. And also these methods ignore spatiality as well as the latent structure in the data. So with this motivation, we try to develop a predictive Bayesian spatiotemporal model for real surveillance data. Mainly, we try to incorporate more recent information with the calibrating discounting factor through the weighted adjustment on their likelihood. So this is our methodology. So I'm not going to explain all the equations. So as our main equation, we use the conditional generalized Poisson distribution framework for the multivariate count time series data. So we focus on the spatiality as well as the time dependency. And mainly we focus on this joint distribution. So as I mentioned earlier, our main focus was adapting a likelihood weight WSD into this joint distribution. So by using the adjacency matrix, we incorporated with the specialty. And so this is the main framework. So here, as I mentioned earlier, our method mainly focused on the population density. So based on the log population, we divided all the counties into two parts, the small county as well as the larger county. So we started with our training window, then we did this iterative process. So let me introduce this iterative process in briefly. If we have a small county, that means with the small population, so we incorporated with the uniform weight. That means we consider W equals to 1. That means to do our predictions, we consider all the historical data. On the other hand, if we have a large county, that means if the county has a large population, we are not going to incorporate with all the historical data to do our prediction, but we use our EWMA weights as described earlier. So why we are going to use this one? If we have a large population, it is better to consider only the most recent data to do the predictions. So after that, we combine this weighted data across all the different counties. Finally, we fit our spatial temporal method using INLA. So why did we use INLA method here? It is because of the computational efficiency. Then we try to predict one step ahead predictions for day t plus 1. And similarly, we did this one iteratively until we observe the maximum number of days. Okay, so let me explain the simulation study. For the simulation study setup, we needed to think about the parameters to fit our spatiotemporal model. So here we use the pre-outbreak data from the MA COVID-19 dashboard. According to their website, they mentioned around day 130, they have an outbreak. So we consider all the historical data to get our parameters. We fit our model. As I mentioned earlier, this is mainly focused on the population density. According to the log population, we divided our counties into two parts, small and the large counties. The selected counties can be considered as the smaller counties. And then we did our predictions up to 200 days. Okay, so these are the simulation findings. And here, as I mentioned earlier, we change our alpha values from 0.1 to 0.9. And we did predictions and we calculated RMSC. Based on the RMSC, we calculated the percentage improvement compared to the uniform smoothing. So we did change the different SNR values. So that means we added different noises for our data, and we also consider 3 different outbreak stages: early, middle, and the late. In each situations, by looking at all the results, so finally we could come up with the optimal alpha value. So based on the percentage improvement, we selected alpha equals 0.1 and 0.2 as our optimal values for our hybrid mixture modeling. Why? Because these two alphas, especially based on the RMSC, reduced up to 60% at higher SNR values. So then we applied these two optimal alpha to our real application. Again, we use the real data based on the similar data set, but we consider whole data set according to their dashboard. So here we consider Massachusetts COVID-19 data, and we fitted our model and we did predictions up to 200 days. So this figure provides the corresponding RMSC improvement county-wise. Here I mentioned the total percentage improvement for alpha equals 0.1 and 0.2. Here you can see that both methods, both alphas use high positive percentage, which implies our proposed mixture weighting procedure outperform the standard uniform smoothing. Again, if you are going to consider the individual counties, again, the most of the counties, individual counties have the positive higher improvement, which implies our proposed method outperform the uniform smoothing. So as a conclusion, so here we incorporated with the likelihood weighted smoothing, and based on the simulation study as well as the real data application, we can say that, okay, our proposed method outperforms uniform smoothing, and also it adapts dynamically to population and the time window changes, and it provides a balanced timely predictions of daily case count. Here we only focus on the predictions, but as our future works, we are going to extend by using the proposed method for the outbreak detections as well as the cross-disease application. Okay, so this is end of my presentation. Thank you so much.
Thank you so much, Dr. Jayawira. Dr. Kalini Jayasinghe, our next speaker, cannot come due to some conflict, but she sent me a recording, so I will be playing that recording to everybody. And we're running short on time, so I'll try my very best to monitor that. Thank you.
Good morning, everybody. Today I'm going to present my research work. This is a collaborative work with Dr. Zasanaika at Wittenberg University. In this study, we can use the Amazon dataset, Amazon 2018 dataset by Ni et al. And it has the overall product rating, the verified status, the review time, review-related information, and the review and the summary. And in this study, we only considered 5 categories because we cannot combine all of the categories together in the training model. To narrow it down, we use only 5 product categories. And when we consider the Amazon review dataset, it has the verified status that one has, whether it is a verified purchase, something like that. When we say the verified purchase label, that status is mentioned in this dataset, and non-verified purchase mean we don't have any label, then it goes to the non-verified purchase. But it doesn't mean that all of these verified purchases are non-fake and non-verified purchase reviews as fake. Most of the previous studies about the fake review analysis, such as the Yelp dataset, they have the labels as fake and non-fake reviews, but this dataset, the Amazon dataset we have, it doesn't have any fake and non-fake label. It only has the verified purchase status and the non-verified purchase status. So in our study, what we did was, first we modify our dataset with the verified and non-verified, using the verified and non-verified signs to label them as fake and non-fake. And then we use the modified dataset to train a neural network model to classify each review as a fake and non-fake review. So the modification part, we had 2 steps. The first one is we consider all of the reviewers and consider their reviews. If any reviewer has more than 50% of non-verified purchase, that means that reviewer will be a fake reviewer. So we considered all of the reviews written by that reviewer as a fake review. Then the remaining verified purchase reviews, we considered them as non-fake. And the second step is to identify which non-verified purchase reviews as fake. In that case, a previous study by Kaufman et al., they label the reviews based on the cosine similarity value. If it is greater than 0.85, they label it as a fake review. But the problem is, why do we need to use that 0.85 value? How do we obtain that 0.85 threshold? And another question is, if 2 reviews are closer to each other, which review will be labeled as a fake review? To address that issue, what we did was we generated 500 computer-generated reviews that we use in the GPT-2 model. Those 500 computer-generated reviews are fake reviews that was generated using the non-verified purchase review in that Amazon dataset. And then what we did was we obtained the cosine bootstrap distribution of the cosine similarity by resampling 100,000 bootstrap samples of sample size 500, and then we obtained the lower 95% lower bound of the bootstrap distribution, and that is 0.76124, and that is the threshold we use for our study to label the non-verified purchase as a fake review by comparing it with the verified purchase reviews. And after we have the modified dataset, our goal is to automate the classification of identifying the fake and non-fake reviews of the Amazon product reviews. So we use the convolutional neural network model. We train that model embedding the features such as the rating, the review length, the sentiment score of the review, and the sentiment score of the summary. We use the pi-fold cross-validation to evaluate the model performance. These are the results we obtained, and here we compared our results based on 5 loss functions, and the haste loss function was introduced in our study. It is the hybrid adaptive cross-entropy loss function. And that loss function performed well compared to the other loss functions. All of them have high, the precision is high, the recall and the funny score, as well as the ROC value. And then we test the accuracy for the testing data based on this haste loss function for all of these 5 categories we had, and all of them performed well. They have good precision, the recall and F1 scores are high, except for the software category. So if you are interested more about this study, we have the newly published paper at Neural Computing and Application. This is freely available, and you can read this article and have more idea about this work. So that's it about my presentation, and thank you for listening, and have a good day.
So that is the end of our session. Thank you everyone for your attention. And yeah, thank you so much, the organizer, for having us. It's a morning in America, so good morning and thank you again.